All right. Oops, I have too many electrons on here. See that? Gave it 10. It doesn't get 10, it gets 8. All right, and the other one that I can draw looks like this. So the question you might ask is, well, which one is it? But they're both equally correct. In reality, they sort of combine and they give you more of a hybrid structure, which would be more like 1.5 bond on each side, which sounds crazy because how can you have half a bond? When they're talking about half a bond, they don't really mean half a bond. What they mean is that when they measure the length of the bond, it's intermediate between a single bond and a double bond. All right? So it's really more like two 1.5 bonds than a single bond on one side and a double bond on the other. Alright, so in Lewis structures, the electrons are localized. What that means is that I have element X, and I'm saying that the electrons are right there. But in reality, what you have is you have element X, and you just kind of have this, like, an area where you will find the electrons around it. So delocalized means that it's not just on one, but it can be on multiple. So, for example, if I have carbon dioxide, like this, it looks like I have a lot of electrons here and I have lone pairs here and here, but in reality what I have is, even though there are electrons in this bond, I kind of have electrons over the whole thing. They may spend more time on one side than the other. For example, if I have water, that's a polar bond, and these are partially positive, this is partially negative. So the electrons may spend more time in this part of the molecule, but they will be delocalized all over the whole thing. So they're not located in just one spot. But when you draw the Lewis structures, it's hard to draw something delocalized, especially when you're drawing a Lewis structure. So you just need to kind of understand that it is delocalized, and that even though this is a good method, it does have some drawbacks as well. Alright, so you get a resonance hybrid. And this shows better that it has resonance. For example, if you have ozone, you would draw like this, and that kind of indicates that you have an intermediate bond there, those little dots. For example, let's say I have a dog. I'm sorry about my art. With a big fluffy tail. So I have a dog. And then I have a wolf. Wolves are bigger. They also have big fluffy tails. They look a lot like dogs. They have longer snouts. This is a wolf. And let's say they have a puppy. Then they have a wolf dog hybrid. So hybrid just kind of means something in between. Something that's in between this and in between that. Something that's kind of a mixture of things. The more resonance structures you can draw, the more stable something is. It's because resonance lowers the energy. Resonance is stabilizing. All right, so in some cases you can draw more than one structure, but they're not equal. So for example, in the structure we had a minute ago, this structure, not that structure, this one right here. In that structure we have, we have two equivalent options. Sometimes we have more than one option and we have to decide which one is the better option. So how do we figure out which one is the better option if we have two options that are not the same? And the answer to that is we calculate the formal charge. And that is the charge an atom would have So the charge an atom would have if the electrons were shared equally. In other words, for formal charge, we kind of ignore the fact that some of it's partially positive and some of it's partially negative. We just say these electrons are associated with this atom in this Lewis structure, so we're going to assign them to that atom. So to do that, here's the formula for that, and you need to know this. Formal charge equals the valence electrons minus 1/2 of the bonding electrons. There's another way that you can write that. Which is the same. So you can either do half of the bonding electrons or just count up the bonds and subtract that. So there are some rules for formal charge. So the sum of all the formal charges should add up to equal the molecule's charge. Now, generally, molecules aren't charged, that's ions. So what it's saying is when you have a molecule, those are neutral, so when you add all the formal charges up, that should equal 0. Or in the case of an ion, like a polyatomic ion, like carbonate, when you add up the formal charge of carbon and the formal charge of all 3 oxygens, it should equal -2, because that's the charge. Or if I had carbon dioxide, which is a molecule and not a polyatomic ion, when I add up the formal charge of carbon plus the formal charge of the 2 oxygen, that should equal 0, because if I look up here, there's no charge, which means that it's neutral. The second rule is the smaller formal charge is better than larger ones. And I'll show you what that means in a minute. And the third one is that negative formal charges should be on the electronegative atom. So let's take a look at an example. So if hydrogen cyanide, and if we look carefully at this, we can tell that one is already a better structure than the other, because remember, the central atom has to be the less electronegative atom. So if you're looking at the periodic table, the most electronegative atom is here, and that's fluorine, and the least electronegative atom is here, and that's francium. So as you go this way, it increases. And as you go this way, it increases. So if I have nitrogen, which is about here, and carbon, which is about here, let me make sure if that's right before I go on with this. I'm pretty sure that's right, but I'm not looking at a periodic table. And I'd hate to be thinking that I'm right and getting it wrong. Yeah, that's right. And then there's oxygen in the middle. So that means that this is the less electronegative atom between carbon and nitrogen. Hydrogen can't be the central atom because it can only take 2 electrons, so it's always on the outside. It's what's called a terminal atom, which means it's on the outside. So if carbon is supposed to be the central atom, then already we know that this is the correct structure and this is not. But we're just going to use this for an example. All right, so we're going to start by counting up the valence electrons. Then we're going to look at how many lone pairs something has. And then we're going to look at how many bonds it has. And I want you to look at this right here. So that has 3 bonds. It also has 6 electrons in those bonds. And if we do half of the bonding electrons, that equals 3. So if you just want to do bonds instead of bonding electrons, it's probably going to be easier. So for hydrogen, hydrogen's in group 1, and everything in group 1 has 1 valence electron, and 2 is 2, and 3 is 3, 4, 5, 6, 7, and 8 valence electrons. So this is in group 1, so it's got one valence electron. Carbon's in group 4. Nitrogen's in group 5. Hydrogen in group 1. Nitrogen group 5. Carbon group 4. And we're looking for lone pairs. So on the hydrogen, there are no dots, so there are no lone pairs. Carbon has no lone pairs. Nitrogen has two, well, when I say lone pairs, I mean lone pair electrons. Let me make that more clear. Lone pair electrons. So, so nitrogen has two. It has one here and one here, so that's two lone pair electrons. This hydrogen has none. This nitrogen has none. This carbon has two lone pair electrons here and here. So then we're going to look and see how many bonds are attached to them. Hydrogen has one bond attached. Carbon has this bond here and then a triple bond on the other side, so that's 4 bonds. Nitrogen has 3 bonds in that triple bond. Hydrogen here is the same, 1 bond. Nitrogen has 4 bonds attached, and carbon has 3 bonds attached. So the formula for that is that we're going to take the valence electrons minus the lone pair electrons, or that doesn't make any sense there. The lone pair electrons minus the bonds. You may also see it written as valence electrons minus lone pair and bonds. But when you distribute this negative sign here and here, then you're going to end up with this formula right here on top. All right, so let's do that. So hydrogen has one valence electron. We're talking about this guy here. And it has one valence electron minus no lone pairs, so we're at 1, minus the bond, which is 1, so we have 1 minus 1, and that's 0. For carbon, let me get rid of some of these arrows. We're talking about this carbon. It's got 4 valence electrons minus no lone pairs, no lone pair electrons, so that's still 4, minus the 4 bonds, and that gives us 0. Then we have nitrogen, this nitrogen, and it's got 5 valence electrons minus the 2 lone pair electrons, so that's 3. And then we subtract 3 from it, and we get 0. So this is nice because they're 0, 0, and 0. So the formal charge for this is 0, this one is 0, this one is 0. So now let's see what happens with the other structure. So we've got hydrogen over here. Erase these arrows because we're moving to the next molecule, or the next drawing of the molecule. So hydrogen is 1 valence electron minus no lone pair electrons, so that's still 1. 1 minus 1 bond is 0. Nitrogen is 5 valence electrons minus no lone pair electrons, so that's still 5. And 5 minus 4 is positive 1. Now we're moving to this carbon here, and the carbon is 4 valence electrons minus 2 lone pair electrons, so that's 2. 2 minus 3 is negative 1. So when we're looking at these 3 and we add them up together, 0 plus 0 plus 0 is 0. And this thing is neutral, so it all equals 0, so that's good. This one is also neutral. And if we add up 0 plus 1 minus 1, we get 0. So that's good. But the thing that's not good, that doesn't follow the rules, is that in this one, is that we have larger formal charges, which is bad. Also, nitrogen is more electronegative, so it should be the one with the negative formal charge. But if you look right here, that's not negative, that's positive. Carbon is less electronegative, and it ended up with the negative charge. Also bad. So more electronegative gets negative charge, or negative formal charge, if there's one to be given. But even so, if you have the option between some negative and positive formal charges or all zeros, choose all zeros. Choose the lowest formal charges you can get. Alright, so I think I talked about there were some exceptions to the octet, and I briefly went over those Monday when I did that lecture. So I'm going to go a little bit more in depth with exceptions to the octets. Now, if you're trying to calculate formal charges on something and you get stuck, please feel free to email me. I am very glad to help you. Not getting a lot of questions from the class, so I just want to make sure that everybody's aware that I am here for you and that I am very glad to help. Alright, so let's go to the exceptions to octets. So let's start by explaining what an octet is. Alright, so you see the carbon in the middle right here? It's got 4 bonds around it, and each bond is 2 electrons. 4 times 2 is 8. So it has 8 electrons around it. And that's the octet rule, is that it should have 8 electrons around it in general. There are some exceptions to that, and the first one that you already know about is hydrogen. And it is set with 2 electrons. There's another one, and that's boron, and it is usually happy with 6. Now boron doesn't have to have 6, it could have 8, but hydrogen cannot have more than 2. So this set is called incomplete octet. Right. Then we also have expanded octets. And the elements that can have expanded octets don't always have expanded octets. They sometimes have expanded octets. And they would be all the elements in the third row, also called a period, and a row just is this direction. So a row in the third row and beyond can have expanded octets. All right, so let me show you what that means. So if we're looking at the periodic table, and we're wanting to look at the periods, we've got 1, 2, 3, 4, 5, 6, 7, so forth. And this is the first row, no expanded octet. Second row, no expanded octet. Third row can have an expanded octet. Fourth row can have an expanded octet. Fifth row can. Sixth row can. And seventh row can. So anything from the third row and below can have an expanded octet. Doesn't mean it always has an octet. It's just capable of having an expanded octet. And so your question might be, well, how on earth am I supposed to know when it has an expanded octet if the rule is that it could, but it might not always? And that just kind of falls together when you draw the Lewis structure. So we will see about drawing some expanded octet rules. There's another one that's an exception to octets, and that is free radicals. They're very reactive. They're odd-numbered electron species. And by species, I mean molecule. So, I wonder if I can change the color on this. Ooh, cool, I can. All right, so we've got this option. And you see how it's just got one electron there and not two? That's what makes it a radical. This can happen. They're very reactive. You've probably heard of commercials where they're like, this gets rid of all the free radicals in your body. They talk about free radicals as not being good because they're so reactive. There are some situations where, you know, people are doing an experiment and they're hoping that they have a free radical because they want it to be reactive. But free radicals can sometimes be explosive because they react so well. And the reason is because atoms are not stable with an odd number of electrons. They're stable with an even number of electrons, for the most part. All right, so let's move on to the next section. If you have any trouble with that, let me know. Oh, there was another one. Let's go back a page. Here, and that was beryllium. And I don't remember the number of electrons that it's satisfied but it can have an incomplete octet as well. So we'll kind of expand this down here. Ugh, it crashed again. Okay. That is okay. It can crash if it wants to, as long as it opens back up. All right. So let's talk about bond energies and bond length. All right. So by bond length, I mean how long is the bond? How long is the distance between one atom and the other one? By bond energy, I mean how much energy is stored in a bond. So one thing that you need to know is that it takes energy to break bonds. Just like if you had two magnets, let's say we have two neodymium magnets, those are the super strong ones that you might have seen in chemistry class or physics class or something like that. You have these two strong magnets together and you want to pull them apart. That's going to take some energy to pull those things apart. Just like if you're going to pull two atoms apart, that's going to require some energy. A lot of times people say that there's energy stored in a bond, so you think, well, when I break it, that's going to release it. Because if I have a glass container and it's filled with diamonds and I say my glass tube contains this many diamonds, if I break my glass tube, the diamonds come out. But that's not the way that it works with breaking bonds. Breaking bonds is more like pulling apart two magnets than it is breaking glass and releasing something. So if breaking bonds requires energy, that means making bonds produces energy. Not produces, but it will give off energy. And that makes sense, even with the magnet idea. If you get the magnets close enough to each other so that they can feel the pull of the other magnet, then they're going to snap together on their own without any energy input from you. So that's the way bond energy works. And there's a formal definition of bond energy. All right. Bond energy is the energy to break, the energy required to break 1 mole of bond. A number of things, just like a dozen. People look the number of things. So if you have 6.022 times 10 to the 23rd bonds, the energy required to break all of them is called the bond energy. Stronger bonds are more stable. Bond energies are averaged, and I'll tell you why. If I'm looking at an oxygen double bond, it could be bonded to fluorine. It could be bonded to another oxygen. Actually, it wouldn't be double bonded to fluorine. We'll put nitrogen there instead. Could be double bonded to oxygen, could be double bonded to nitrogen, could be double bonded to carbon, could be double bonded to a bunch of different things. And all of these things have different electronegativities, which mean some of them pull electrons away from oxygen and some of them don't. So that means the bond energies are going to be slightly different. So the energy required to break those bonds is a little bit different. So what they do is they do an experiment. They break bonds of a whole bunch of different things. They take those numbers and then they average them. To get an average bond energy. So let's go over what bond is stronger. What bond is weaker? What bond is longer? What bond is shorter? These are always nice questions to have on a test because they're super easy and super quick. All right, so we have double bonds. We have, well, I should start actually with triple bonds. Then we have double bonds. And single bonds. And your question might be, well, is there a quadruple bond? There might be somewhere, but I've never seen a quadruple bond. So we just go single, double, and triples. A quadruple bond, if there is one, would be very rare. So you're not going to run into that. So with a triple bond, it is the strongest. It is also the shortest. A double bond is the middle strongest. Or the intermediate strength bond. And the single bond is weakest and is longest. All right, so the strongest one is the shortest one. The longest one is the weakest one. And you can remember this by thinking about sitting in the grass next to a tree. So we've got the ground. We've got a tree. Right? And this tree has branches. And a tree that has branches will have sticks laying on the ground. And you might be sitting or standing by the tree. And you're happy. So you're sitting there, but you're a little bored. So what do? You pick up a stick. So then there's you. And you have a stick. You have a long stick. And you break it. And then there's you with a shorter stick. Let me make that a little shorter. And it took not a lot of energy to break the long stick. So now there's you. And you break this one. Apparently you grew taller too. And then now you have a kind of a probably a little shorter than that. You have a short stick. And you go to break the short stick. And it's harder to break it. And this would be the next hardest. And this would be the easiest. This is also the shortest. Takes the most energy to break it. The next one is the middle. And this one is the longest. And it takes the least energy. So you have a stick. All right, so you have the first stick, you break it, you have about half as much stick. You break it, you have about half as much stick again. You try to break it, it's harder. And you could also think of this as if you had a pencil and you broke your full length pencil and you break the pencil in half, then you have half a pencil and you try to break the half a pencil in half, and then you have just this little piece of a pencil. Try to break the little piece of a pencil in half. It's going to be very hard. The shorter it is, the more energy it takes to break it. It's the same with the bonds. So with the bonds, you have a single bond that is the longest. You have a double bond, which is intermediate length. And then you have a triple bond, which is the shortest. This is strongest. This is weakest. And this is intermediate. And that would be double, single, and triple bonds. All right. So now I need to look at something. Give me just a second here. All right. So now we're going to start to get into VSEPR theory. Before we get into VSEPR theory, I'd like to take a minute to do some examples of Lewis dot structures so that we get some practice in on that. I'm trying to bring up the e-text on my other computer. It should have some good examples in it, but it's rather slow to load. Come on, book. Let's see. All right, so what I'm going to do is I'm going to go to chapter summary. No, I'm going to go to exercises at the end of chapter 4. I'm going to pass by the review questions and get to the problems by topic. And I'm going to do some, some Lewis dot structures for some compounds. There should be some in here. Got some naming stuff. Lewis structures, formulas, names of molecular compounds. Trying to look for some more complicated ones. Maybe there are some in chapter 5. Yeah, there should be some in chapter 5. Alright, so I'm going to go to Chapter 5 exercises at the back, at the end of the chapter. I'm going to pass by the review questions. Going to go into the problems by topic, pass electronegativity and bond polarity, and get into the writing structures, resonance, and formal charge. We'll do a couple of those as practice. All right, so let's take a look at number 28. It's got NF3. We're going to draw the Lewis structure for that. So nitrogen, first let's figure out what's the central atom. This is less electronegative, so it goes in the middle. The next thing we're going to do is we're going to connect all of the other atoms. All right, now we're going to count up valence electrons. Nitrogen's in group 5. There's 1 nitrogen. Fluorine is in group 7. There are 3 fluorines. That's a total of 26 electrons. We've used 2, 4, 6 electrons. That's going to leave us with 20 electrons. So now we're going to take and fill up the outside elements with octets. It already has 2, so 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh gosh. Let's see. 3 times 6 is 18. I don't know what I'm counting. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18. All right. So we've used 18. We have 2 left over. Get rid of all these little arrows so you can see better what we're doing. All right, so what do we do with these leftovers? Do we put them on fluorine? If so, which one? Well, we don't. Because once the outside ones have an octet, if you have any leftover, they always go on the central atom, which in this case is nitrogen. It doesn't matter if it pushes it over an octet. All right, so this is the structure for NF3. So let's calculate the formal charge for these. Let's start with nitrogen. It's the valence electrons, which are 5 because it's in group 5, minus the lone pair electrons, it has 2, minus the number of bonds, it has 3. So 5 minus 2 is 3, 3 minus 3 is 0. Now, all 3 of these fluorines are identical. They all have 1 bond and 6 lone pair electrons. They're all in group 7, so we really only have to calculate one of them because the other 2 will be the same. Fluorine is in group 7, so it has 7 valence electrons. It has 6 lone pair electrons, those are the dots around it, minus the 1 bond. 7 minus 6 is 1, 1 minus 1 is 0. 0 plus 0 is 0, which equals the charge of NF3. All right, so the formal charge for nitrogen is 0, and each fluorine is 0. All right, so let's do another one. I'll look and see if there's one that they have with an expanded octet. Before we do that, I want to do one of the ions. So if you go down to number 35 in problems by topic, it says write a Lewis structure that obeys the octet rule. For each molecular ion, include resonance structures if necessary, and assign formal charges to each atom. All right, so this is number 35. And we're going to do B, which is CO3 2-. First, we're going to find the least electronegative atom, which is carbon. It's going to go in the middle. We're going to connect the oxygen to it. Now we're going to count the valence electrons. Carbon's in group 4. It has 4 valence electrons. There's 1 carbon. Oxygen's in group 6. There are 3 oxygen. And then if you look here, we've got a 2- charge, so we're going to add 2 electrons to it. So that's 14. That's 4, not 14. It's 4. 18 and 2 is 20. 20 plus 4 is 24. All right. So we've used 6 because we have 3 bonds already. So that leaves us with 18 more. So we're going to fill up the outside electrons. We've used 18. We don't have any leftovers to go on carbon. If you look at carbon, carbon has not got an octet. So we're going to need to borrow 2 electrons from somewhere. When we borrow 2 electrons, we have a choice of any of these 3 oxygen because they're all identical. There's nothing different about them. They're all exactly the same. So we're going to start right here on the right, borrow 2 electrons and make a double bond. So since it's got a charge, we're going to put it in brackets and put the charge on the outside. This clearly has resonance because it is 3 identical oxygen. So we're going to draw the 3 other options. And then the last one. And like I said before, when you're drawing the dots, for example, if you're going to be drawing the dots around, let's say this oxygen here, it doesn't matter if I put the dots there or if I put some at the end like this, or I put them over there, but I just want to make sure that I have 4. I like to put them 2 on each side, but you don't have to. You can put 2 on the side and 2 on the bottom, just as long as you're putting them in pairs. All right, so now we want to calculate the formal charge. We've got to calculate the formal charge for carbon, 1 oxygen with a double bond, 1 oxygen with a single bond, because these 2 are the same. And if you look at all the other structures also have 1 double bonded oxygen and 2 single bonded oxygens and a carbon. So let's go and start with carbon. It has 4 valence electrons, no lone pair electrons, and 4 bonds. So carbon is 0. So I'm going to put a little 0 by the carbon. Now we're going to do the double bonded oxygen. All right, so oxygen is in group 6, so it has 6 valence electrons, minus 4 lone pair electrons, minus 2 bonds. 6 minus 4 is 2. 2 minus 2 is 0. Oop. All right, so I'm going to put a 0 next to that guy. Now I'm going to do the other oxygen. It's going to be the single bonded oxygen, and that has 6 valence electrons, minus 6 lone pair electrons, minus 1 bond. 6 minus 6 is 0. 0 minus 1 is -1. So I can fill that in for all of these. Now I have to add up the formal charges to make sure they equal my charge, which in each case is -2. So I have 0, 0, -1, and -1. -1 and -1 is -2. So I've satisfied all of those rules, and I need to make sure that the negatives are on the more electronegative atom. And they are, because oxygen is more electronegative than carbon, according to our periodic trend. So our periodic trend is this. It increases going up, and it increases going this way. Fluorine is the most electronegative, and francium is the least. All right, so let's see what else we've got. All right, so I've scrolled down to number 45. That's odd electron species, incomplete octets, and expanded octets. So these are the exceptions. Now, you won't have a test question that's listed under a section called odd electron species, incomplete octets, and expanded octets. You'll just be assumed that you can draw the structure for it and that you'll know that it's fine with an incomplete octet or something like that. All right, so let's do number 45. A. All right, that is BCl3. Boron is less electronegative than chlorine. Boron goes in the middle. We connect the other chlorine. And then we have to figure out the valence. So boron is in group 3. So it has 3 valence electrons. Chlorine is in group 7. There's 1 boron and 3 chlorine. So that's 3. This is 21 for a total of 24. We've used 6 in the bonds that we made. Leaves us 18. But oh no, boron doesn't have an octet. Boron is an exception, so I'm not going to make a double bond. Boron is satisfied with 6 electrons. It's good. So this structure is all I need for this. All right, so let's take a look at another one. Let's take a look at NO. All right, there's not really a central atom because there are only 2. Nitrogen's in group 5, oxygen's in group 6. There's 1 of each. Gives me 11 electrons. Should be able to tell at this point that you're going to have a radical. All right. So we've used 2, and that leaves us 9. All right. Oxygen is more likely to have pairs than nitrogen. So if you have to choose between nitrogen and oxygen for a radical, nitrogens tend to get the radicals more than the oxygens. And oxygens can get the radicals too, but you know. All right, so we've used 2, 4, 6, 7, 8, 9. All right. Nitrogen doesn't have anywhere near an octet, So we are going to double bond here. Now oxygen has 2, 4, 5, 6, 7. Nitrogen has, oh, my stupid thing froze up. Hang on a minute. Okay, nitrogen has, oh, it's still frozen. And, no, it's not frozen. I had it on eraser. Oh. Okay, nitrogen has 7, and oxygen has 8. And that's the best we can do. That's it. Now we can look and decide also where the radical goes based on what's more electronegative and what's less electronegative based on formal charge. So nitrogen's in group 5, minus the 3 lone pair electrons, minus the 2 bonds is 0. Oxygen is group 6, so 6 valence, minus 4 lone pair electrons, minus 2 bonds, which gives us 0. So we have a good structure here. We have 0 and 0. Now let's draw it the other way. Where we start like this, and then we make a double bond, and we count up. Nitrogen has 8, oxygen this time has 2, 4, 6, 7. So let's do, that is 7 electrons surrounding it. So let's do the formal charge for the oxygen. The oxygen is 6 valence minus 3 lone pair minus 2 bonds is plus 1. Nitrogen is group 5 minus 4 lone pair minus 2 bonds. That's -1. So this would be -1 and this would be plus 1. There are 2 things wrong with this structure. One is that if you have an option between this structure, which has formal charges of 0 and 0, and this one that has formal charges of plus 1 and minus 1, that's bad for the higher formal charges. So you want to go with the lower ones, the 0 and 0. Also, the negative should be on the more electronegative atom. This is the more electronegative atom, but it has the more positive charge. So that's wrong also. All right, let's see. Let's do number 50, letter D. And that is IF5. All right, so can't say the word, iodine is less electronegative than fluorine. So iodine is in group 7. We have 1 of those. Fluorine is also in group 7. We have 5 of those. 7 and 5 is 12. So we have 42 electrons. We've used 6. That leaves us not 32. That would be if we had 10. So that leaves us 36. So we're going to surround, you know what? Let me start over. See what I've done? There are 5 fluorine, and I only put 3 on there. Let me add the other 2. There we go. Now we can do something. All right, this was what, 42? All right, now we have used 10, which will leave us 32. So we're going to put 6 electrons on each of the fluorine. All right, and 6 electrons per fluorine. We have 5 fluorines, so that's 6 times 5. So we've used 30. We have 2 left over. Should we really put these 2 leftovers on iodine? Iodine already has 10 electrons. That's 2 beyond 8. The answer to that is yes. Because if you have leftovers, you always put them on the central atom, even if it goes beyond an octet. So iodine has 7 valence electrons, minus 2 lone pair electrons, minus 5 bonds, 0. Fluorine is in group 7, so it has 7 valence, minus 6 lone pair electrons, minus 1 bond is 0. So this is 0, 0, 0, 0, 0, and 0, which is good. All right, and we can also tell that iodine is fine to be beyond an octet, because when we look at the periodic table and we try to figure out what row it's in 1, 2, 3, the 4th row. No, the 5th row. 1, 2, 3, 4, 5. It's in the 5th row. So we got 1, 2, 3, 4, 5, and iodine is like right here. So iodine is well below the 3rd row. So anything that's in the 3rd row or below can have an octet. Doesn't mean it will, but it can. But you see that when we did the Lewis dot structure, it just fell out where iodine had more than 8. So it doesn't matter that I know really whether or not, there aren't really rules where iodine can and iodine can't. Iodine may have more than 8. So when you draw your structure and it has more than 8, that's fine. All right, so let's go on to the next section, and we're going to start VSEPR theory. We're going to start by talking about what electron groups are. All right, there are several different types. A lone pair is one group. Single bond is one group. Double bond is one group. Triple bond one group. Radical, which is that lone electron, one group. Even though a double bond has 2 bonds in it, when we're talking about electron groups, it's considered one group. Electrons all have negative charges, so they have similar charges, and like charges repel each other. And the electron groups on the central atom So the electron groups on the central atom determine the molecular shape. So first you have to draw the Lewis structure, then you have to count up the electron groups on the central atom. So the preferred shape is going to reduce repulsions, and that's the theory here for the valence shell electron repulsion theory, is the goal is to reduce repulsions. All right, so let's start with linear geometry. It has two electron groups. So let's take a look at beryllium chloride. So beryllium's in group 2, chlorine's in group 7. There are 2 of them, total of 16. Beryllium's in the middle. All right, beryllium doesn't have an octet, but it's an exception. So it's fine like it is. So what we're going to do is we're going to count the electron groups around beryllium. Here's one group. Here's the second group. So there are 2 electron groups. No lone pairs. So that means it's linear. The angle for linear things is 180 degrees. So each chlorine is going to be 180 degrees apart from each other. Another example would be carbon dioxide. Carbon's in group 4. Oxygen's in group 6. We have 2 of them. Oop, I'm giving the answer away. Now if we look at carbon, it's not got an octet. It's not an exception to the rule. It's not one of the ones with the incomplete octets. Still no octet. Now we have an octet. So now we need to determine the shape. To determine the shape, we count the electron groups. There are 2 electron groups. There are no lone pairs. That means it's linear with a 180 degree angle. So let's look at when we have 3 groups. All right, so that's trigonal planar. So let's do an example. All right, we did this example a few minutes ago, so I'm just going to draw out the structure. That's the structure. So now we're going to count electron groups. Remember, boron is an exception to the octet rule. It gets an incomplete octet frequently. So it's 1 electron group, 2 electron groups, 3 electron groups. We're only concerned with the electron groups around the central atom. We don't care what's around the fluorine. We only care what's around the thing in the middle. It has 3 lone pairs. Not 3 lone pairs. 3 electron groups. 0 lone pairs. Now, yes, fluorine has lone pairs, but boron has no lone pairs. And that's what we're looking at, boron. So that means it's trigonal planar. Which means it's going to be in one plane. So in this case, it's in the plane of the paper. So I'll kind of draw a ball and stick structure here. And this is kind of, if you draw a line around these, it's going to be a circle. A circle is 360 degrees. We have 1, 2, 3 areas, so we've got to divide that evenly by 3. Leaving us 120 degrees. So trigonal planar with 120 degrees. All right. So let's do another one. We have CH2O. All right. Carbon is going to be in the middle. Now this oxygen here is written right next to a hydrogen. So do I put it here? No. Hydrogen can only take 2 electrons. I put it here. So if it's written like that, the oxygen goes on the carbon. They frequently put the hydrogens in the middle of the formula, but all that stuff goes on the carbon. So we have 4 from carbon, 1 times 2 from hydrogen, 6 from oxygen, there's a total of 12. We've used 6 in our bonds, leaving us 6. And we can't put them around the hydrogen because that's a no-no. We can only put them around oxygen. Then we have to check the middle one for an octet. Carbon can take an octet. It doesn't have one. So we're going to borrow these electrons here and move them. Have a double bond. All right. Now you couldn't have resonance here because carbon to hydrogen is 1 bond. Hydrogen can only take 1 bond. So you couldn't have like a carbon-hydrogen double bond. So this is your only option for this. So let's count the electron groups. And remember, a single bond is 1 group. So that's 2 groups. And a double bond is also 1 group. 1 group, 1 group, 1 group. Total of 3 groups. No lone pairs. So that's trigonal planar. And 120 degrees. All right. So now let's look at 4 groups. So far, the only angles we've had are 180 and 120. They're both 360 degrees divided by however many sides you have. So with the linear, you have 2 sides, the top and the bottom, so that's 180 degrees. With trigonal planar, you have 3 sections, so that's 180 degrees for linear, 120 degrees for trigonal planar. So now let's look at another group. 4 groups, no lone pairs is called tetrahedral. Remember, tetra means 4. Alright, and the angle is 109.5, and yes, you have to memorize that. You have to memorize the names and the angles. Alright, so let's take a look at an example. Here's an easy example. Alright, let's count up how many groups we have. 1, 2, 3, 4. All right, and its shape looks kind of like this, with one hydrogen going into the page, one in the plane of the page, and one kind of coming out at you. So when you see this, this is called wedge and dash. It's a wedge and dash structure. Note that the ones that look like this, they're imitating something that's harder to see. It's harder to see because it goes away from you. And then when you see this one is easier to see. It's completely filled in. You get the idea. So, and that's coming toward you. And a straight line means in the plane of the page. So you may have some questions. Given a wedge and dash structure, somebody might, identify this hydrogen and say, well, is it going into the page, out of the page, or in the plane of the paper? And the answer would be into the page. All right, so let's take a look at 5 groups. All right, we have PCl5. All right, so that's PCl5. So let's count up electron groups around the phosphorus. 1, 2, 3, 4, 5. These are trigonal bipyramidal. And these have one part of it where it's a trigonal planar section around the middle. And then you have something that goes straight up, something that comes straight down. So the angle here is 120 degrees, and the angle here is 90 degrees. So there are 2 angles here. Technically, you could say, and the angle from here to here is 180, but they don't usually bother with that one. But technically, that's correct. Let's take a look at octahedral. And octahedral is a little tricky because octa means 8, but we don't have 8 groups, we have 6 groups. I don't know why they call it octahedral, they just do. I think they should call it hexahedral personally, but they don't. Octahedral looks like this. You've got a straight up and down part, just like the other one. And then you've got one here, one coming out at you, another one coming out at you, like that. So the angle here is between these two is 90 degrees, and the angle between these two is also 90 degrees. So the angles are 90 degrees. An example is SF6. Sulfur is beyond group 3. So it can have more than an octet. Alright, so that's SF6. And one thing to note, when you draw the Lewis structure, the way it looks, does not mean that you go by what it looks like to be the shape. You have to count the electron groups around the central atom. All right, so that's octahedral. All right, so let's do an example. Let's do NO3 minus, nitrate. All right, so nitrogen's group 5, oxygen's in group, I keep doing that, oxygen's in group 6, and we have a negative charge, so we have to add one extra one. If you had a positive charge, you would subtract one. So, for example, if we had NH4 plus, and we're trying to add up the valence electrons, that's nitrogen. This is hydrogen. And then the positive charge, you have to subtract one. So if you have a positive charge, subtract. If you have a negative charge, add to get the valence electrons. Just for Lewis structures. Oh, goodness. My phone is ringing. That I will have to take care of later. All right. So let's go back to our example. So nitrogen's less electronegative. It goes in the middle. Oxygen. Oh, this was 24. We used 6. We're left with 18. We're going to end up with resonance here. So you could draw it like that. You could draw it like this. You know what? That's a few too many. So there are those three options. That's resonance. So it's stable. But to figure out what shape nitrate is, we've got to count the groups around it. And we're only going to count groups around one of the resonance structures. Doesn't matter which one you pick, they're all the same. They all have three groups around them. All right, so that's that example. If you were going to do NH4, that is 4 groups. So it's tetrahedral. It's 109.5 degrees. All right, so let's see what happens when we do have lone pairs. Because remember, I'm writing how many groups, and then I write no lone pairs. How many groups, and then no lone pairs. What if you do have lone pair? Then what? All right, an example of that is NH3. That's for nitrogen. That's for hydrogen. Nitrogen goes in the middle because hydrogen can't. All right. So let's take a look at this. There are two things we need to look at here. The total number of groups. 1 group, 2 groups, 3 groups, 4 groups. And so if you're looking at the groups without paying attention to the lone pairs, you're looking at electron geometry. And the electron geometry, we know 4 groups make something tetrahedral. But the lone pair affects the angle because the lone pair has nothing attached to it, so it kind of takes up more space and it pushes the hydrogens closer together. So the angle is less than 109.5 because of the lone pair. Now, let's say we're not interested in the lone pair too much. We want to know what is the shape of the nitrogen with the hydrogens. Then it still has 4 groups, obviously. And one of those groups is a lone pair. That has a particular molecular geometry. And that is trigonal pyramidal in this case. All right, so in this case, we have something here, then we have something sort of coming toward you, something else coming kind of toward you, maybe one in the plane of the paper, making a little tripod kind of, and then this lone pair at the top, giving it a typical tetrahedral shape, but the nitrogen with the 3 hydrogens gives it more of a tripod shape, like that. If we include the lone pairs, that would be tetrahedral. All right, so molecular geometry considers only bonding groups. There's a time when the number of when your electron geometry is the same as your molecular geometry, and that's if you have no lone pairs. Then your electron geometry equals your molecular geometry. Molecular geometry. When you have no lone pairs. When you have lone pairs, your electron and molecular geometry are different. All right, so let's do another one. So basically what we're doing is we're looking at things right now that have 4 electron groups. All right, and then we're going to look at things that have 1 lone pair and 2 lone pairs. This is tetrahedral. This is bent. This is less than, no, this is, if you have no lone pairs and you have 4 electron groups, that would be 109.5. If you have a lone pair, that's less than 109.5. And if you have 2 lone pairs, that's even smaller, and that's even more, less than 109.5. So we had this tripod shape with something that goes straight up. That's tetrahedral. And we looked at it when everything was an atom. Then we looked at it when one thing was a lone pair. Now we're going to look at it when we have 2 lone pairs. All right, and the shape between these is bent. The electron geometry is still tetrahedral because we're including all electron groups regardless of whether or not they're lone pairs. But the molecular geometry, it matters about the lone pairs. So it's important that you know the angle for water. You need to memorize that. Might be on your test. Might not, but it might be. Haven't written the test yet. All right, that's the Lewis dot structure for water. So let's count the electron groups around oxygen. So 4 electron groups. And then let's look and count how many lone pairs we have. We have 1 lone pair, 2 lone pair. So that means the electron geometry is tetrahedral. The molecular geometry is bent. And the angle for this is less than 109.5 degrees. think on the previous page. Let me go back and look at that. Yeah. When I did this less than sign, I made it an angle sign. And the same with this. I don't know what I was thinking. It's less than, not angle. All right. All right. So as the lone pairs increase, the bond angles decrease, as we've seen. As the lone pairs increase, the bond angles decrease. All right, so now let's look at something that has 5 groups. That's not the button I meant to hit. All right. So if you have one lone pair, you get something that's seesaw. And the angles are less than 120 and 90 degrees. And then if you have 2 lone pairs, you get something that's T-shaped. And you still have less than 120 degrees and 90 degrees. And if you have 3 lone pairs, you have linear. And the angle is 180 degrees. Let's take a look at those. All right, so let's say we had SF5. That's what it would look like. So if I'm going to draw SF4, I would have to change out one of these fluorine for a lone pair. It matters where I pick to do that, because right here, here, and here is a trigonal planar space. Those are called equatorial. Those are equatorial fluorines. And the other two, the one from here to here, are axial. All right. You need to remove one of the equatorial. So SF4 is actually like that. So that's where we know to put the lone pairs in an equatorial place. So if you're looking at that, what you get is basically you get something that's straight and then going into the plane of the paper is one fluorine, and then coming out of the plane of the paper is another fluorine. So basically you've got something that kind of looks like this, which is kind of like a seesaw. I don't know if you've ever had a seesaw. That's a child's toy that requires lots of trust in your friends, because one child sits on this end and then they push off from their feet, and then this child who's up in the air then goes down. Then they push off with their feet and they go up in the air, and the other one goes down. Inevitably one of them will get off and not tell the other one, and they go flying. Not flying away, but flying down to the ground. So anyway, that's why they call it a seesaw shape, because that's what it looks like. So SF4 had, we didn't count up the groups, had 1, 2, 3, 4, 5 groups. And 1 lone pair. And like I said before, yes, fluorines all have lone pairs. We're not interested in the ones that are around fluorine. We're only interested in the ones that are around sulfur. Right, so let's see what happens when we remove 2 from the equatorial position. So we still have the ones at the axial position. We have 1 equatorial left. Remember, boron is an exception to the octet rule. But in this case, we're going to do bromine instead, so that we can put the lone pairs on it. All right. So we've replaced 2 of the equatorial positions with lone pairs. So let's count groups. 1, 2, 3, 4, 5. 5 groups. So 5 groups is trigonal bipyramidal. What did I put on the other page? Nothing. Okay. That's the electron geometry. The molecular geometry is T-shaped. And the angle is less than 120 and 90. So this is your 90-degree angle, and this is your less than 120-degree angle. All right. Let us replace the last equatorial position with a lone pair. Remember, we still have our axial positions. So let's count groups. 1, 2, 3, 4, 5. 5 groups. We have 1, 2, 3 lone pairs. I forgot to write that this one up here had 2 lone pairs. All right, so 3 lone pairs. The electron geometry is trigonal bipyramidal still. And the molecular geometry is linear. The angle is 180 degrees. I remember why they call it octahedral. But let me show you something with this trigonal bipyramidal. So you have something in the middle, you have something up here, something here, here, and here, and something that goes down. So you could draw a pyramid I've messed up this pyramid somehow. Yes, okay, hang on. Let me try that again. something in the middle, something here, something here, here, and here, something down here. All right, so it goes here, here, here. This goes here, here, and here. So it's not the best pyramid, and it's not the easiest to look at, but it's called trigonal bipyramidal because you have a pyramid on the top and a pyramid on the bottom. And it's trigonal because there are 3 sides to the pyramid. You have the 2 front sides and the back side. So let's take a look at octahedral. That's 6 groups. And they're all 90 degrees. And you have something that's here, and here, and here, and here, and here, and here. It doesn't matter where you put the first lone pair in this case, because everything is 90 degrees away from everything else. But let's see why they call it octahedral. All right, you probably can't tell very well from this drawing, but what it gives you is it gives you a pyramid with 4 sides, 1, 2, 3, and the back side is the 4th side. And you have 2 of those. You have another one. That's 1, 2, 3, and the back side is the 4th side. So it's a total of 8 sides. There are 6 groups, but there are 8 sides. That's what's called octahedral. All right, so let's start removing groups. The first group doesn't matter where you remove it. We're going to draw bromine tetrafluoride. I'm going to put it at the top. You could pick any position for the first one. All right, so let's count groups. 1. Let's draw this lone pair a little differently. I'm just going to put the lone pair close to the bromine so you understand that it's so that you can see better that it's attached to the bromine. So that's 1, 2, 3, 4, 5, 6 groups. And there goes my phone again. Sorry about that, guys. 1 lone pair. So the electron geometry is octahedral. And the molecular geometry as square pyramidal. Give me just 1 second. I want to look something up. hang on. Sorry, I almost had what I was looking for. I'll look it up later. Okay. I do not know why the settings popped up there. Okay, that's strange. All right, so let's remove the next one. Now, oh goodness gracious. There we go, sorry. All right, so let's remove another one. We're going to do xenon tetrafluoride. And this time it matters where we remove the next one. So if we have a lone pair here, then the second lone pair has to be opposite the first lone pair. All right, so let's count groups. 1, 2, 3, 4, 5, 6, and 1, 2, 2 lone pairs. So again, the electron geometry is octahedral, and the molecular geometry is, these are all 90 degrees from each other. Can't do the 90-degree box very well, but anyway, they're 90 degrees from each other. And the molecular geometry is square, planar, because it forces everything to be in a plane, in one plane. So and it basically makes a square. If you connect all the fluorine, then you get a square. This one is called square pyramidal because you basically get something with a square base. And it's a pyramid, so that's square pyramidal. All right, let's see what else are we going to do. All right, so here are the rules for VSEPR theory. Oh, I spelled this wrong. So that's what it means, the VSEPR. Technically, I guess it should be VSEPR, but it's easier to say VSEPR, so that's what we call it. All right, so the first step in VSEPR theory is to draw the Lewis structure. The second step is to count groups. The third is to count lone pairs. And the fourth is to name the shape. And the angle. All right, and that's all there is to that. You may see in some charts they'll have something like electron groups, and then bonding pairs, and then lone pairs, and then electron geometry, and then molecular geometry, and then the shape, or those would be shapes. But so let's say you have something like this. Then let's count the electron groups. I'll show you how to kind of work one of these charts. 1, 2, 3, 4, 5, 6 electron groups. Let's count the bonding pairs. Bonding pairs mean the bonds. 1, 2, or the bonding groups. 3, 4. Now let's count lone pairs. All right. So then your electron geometry would be trigonal bipyramidal. Trigonal. Try to remember how to spell that. And then molecular geometry. And then it'll ask for the angle, which would be 90 degrees. So that's how that's what it means when it's talking about bonding pairs compared to lone pairs. All right, so I want to go over the wedge and dash system one more time. All right. A straight line, whatever direction it's going, could be up, down, but side to side, means it's in the plane of the paper. All right. And then this means it's going away from you. And then this means it's coming toward you. So if I'm going to draw water, and there was one thing, I don't remember if I told you guys this or not, but you need to remember this angle for water. Water has an angle of 104.5 degrees. You need to remember that. Okay? For anything else that's bent, you would just say less than 109.5. But you need to know this angle. All right. So back to what I was talking about with the wedge and dash structure. So we would draw it like this. Oxygen, hydrogen in the plane of the paper, hydrogen in the plane of the paper, wedge going away from you to a lone pair, wedge coming out toward you with a lone pair. And that means that the solid wedge is coming out, the dash wedge is going in, and the lines are in the plane of the paper. All right, so let's take a look at something that's more complicated. Let's look at this. Sometimes you'll be given a structure like this and asked to give the shapes. I say shapes because there are two central atoms. There's carbon, that's one central atom, and then there's oxygen, that's the other central atom. To do that, you really have to know how many lone pairs and how many groups. It looks like there are no lone pairs. These can be tricky because sometimes they leave them out. So the first step in something like this is to make sure you count all the valence electrons. Alright, so we have 4 hydrogen. They're in group 1, so they have 1 valence electron. That's a total of 4. We have carbon, it's in group 4. We have 1 of them, so that's also 4. Oxygen's in group 6. We have 1 of those. That's 6. 6 and 4 is 10, and 4 is 14. Let's count how many we have in the bonds. So this bond is 2, 4, 6, 8, 10. There are 4 electrons that are not showing up. Let's see where they could go. Does carbon have an octet? Yes, it does. It has 8 electrons around it. Does the oxygen have an octet? No. How many electrons is it away from having an octet? 4. You have to put the electrons in pairs. So that's your structure. So just make sure you've always got all of the electrons in there. So let's take a look at carbon first. Let's count its electron groups. 1, 2, 3, 4. Four groups, no lone pairs, is tetrahedral. All right. Let's count the electron groups around the oxygen. 1, 2, 3, 4. Let's count the lone pairs. 1, 2. And with this one up here, this was electron geometry and molecular. And this one, the electron geometry is tetrahedral, and the molecular geometry is bent. A lot of times they'll ask you for the molecular geometry of these, so that's all I'm going to label it with. And the angle here would be less than 109.5. But they don't, to be in a shape like that, they don't all have to be tetrahedral for electron geometry. It could be something that's tetrahedral and then the other one could be linear, or it could be tetrahedral and trigonal planar, or it could be trigonal planar and linear, or something like that. They don't have to be the same. Alright, so let's talk about polarity in structures. We talked about polarity before. Polarity is a difference in electronegativity. Let me move that to the next line because I can't write the word there. It's where part of the molecule is partially positive and part is partially negative. Let's say we have this molecule. Chlorine is more electronegative. Hydrogen is less electronegative. Now there's a special arrow that you draw for polar bonds, and it looks like this. You see the positive part of the arrow, this part right here, goes on the less electronegative piece. And the arrow head goes on the more electronegative piece. So this one is clearly polar. There's a significant difference in electronegativity. You can tell that by looking at the periodic table. Let's take a look at this structure. If you're looking at that, and you look at the place where oxygen is and carbon is, and you kind of get the sense that it's a polar bond, or you could take the electronegativities and subtract them, and that falls into polar covalent for carbon to oxygen. So this one is more electronegative, so is that one, and this is less electronegative, so it's partially positive. So we're going to draw the arrow. Draw two arrows there. What happens to these two arrows? They cancel each other out. So this molecule that has polar bonds is a nonpolar molecule. It has to do with adding vectors. Vectors are quantities with a direction. So with a magnitude and direction. Let's think, for example, if I'm standing right here and I go this far this way, and then I reverse and I go the same distance that way, where do I end up? I end up right where I started. So I didn't go anywhere. I didn't end up anywhere different, that is. Alright, so let's take a look at some different molecules. See if we can recognize if the molecule is polar or not. Alright, so we've got this one. What do you think? So the arrow kind of goes like this. Do they cancel each other out? No, they're pointing in the same direction. They're overall pointing this way. So this one is polar. You can also tell because everything connected to that oxygen is not the same. So let me show you what I mean. This is a bad example. This is just a side note. A carbon to hydrogen bond is nonpolar. Always. So this all has carbon to hydrogen bonds, and the whole thing is nonpolar. Alright, so let's say we have another molecule. I'm going to make something up. This probably doesn't exist. Alright. You know what? That's not what I wanted to do. Well, this might exist. Alright. So, is the carbon